So let's talk about the oblique asymptote. So in an oblique asymptote, an oblique asymptote is an asymptotic line that is neither vertical nor horizontal, but it is at an inclination to the x-axis and is called a slant or oblique asymptote. So in our rational function, we will know that we will have an oblique asymptote if the numerator, the power of the numerator is 1 plus 1 higher than the denominator. So say for example, we have the following rational function. So our rational function here, say p of x is equals to f of x over g of x, where of course g of x is not equals to 0, and where f of x and g of x are both polynomial functions. Okay. Will have or has an oblique asymptote if has an oblique asymptote if the degree of f, meaning the function in the numerator, is exactly one more than the degree of g. Okay, so in order for us to know where or what the oblique asymptote is, what we will do is we will implement polynomial division in order to identify where the oblique or what is the oblique asymptote. So if we do the division, say the p of x, performing polynomial division, the L of x here, which is the answer to our question, plus r of x, meaning the remainder, over g of x, where r of x is the remainder. Okay, and here the oblique asymptote will be this one here. So L of x, or y equals L of x, is the oblique asymptote. Mama. Okay, so for example, remember when we for example in division we have, say let's say 25 divide by 6, right? So of course this will be 4, and we will have 24 here, né? And so this is going to be, subtracting it, this will be 1, and so our answer here will be in mixed number form. It will be in 4, that's the quotient there, plus 1 over 6. So this over here, in this example, this is our L of x. Okay, and in polynomial division, this is going to be our oblique asymptote. And this one here is of course our remainder, or in this in the notation above, that is equivalent to our r of x. Okay, so let's perform a polynomial division for this rational function. So for example, if we have the rational function f of x is equals to x squared plus 2x plus 1. Okay, so with this rational function, okay, obviously because this one here is higher than the degree of the polynomial in the denominator, which is 1, therefore here we expect to get an oblique asymptote. asymptote. Okay, so let's perform first the division. Of course, we can divide this just directly, right? Because we can also write this one as x squared over x plus 2x over x plus 1 over x, right? And this can be simplified into x plus 2 plus 1 over x. Yeah? So, of course, this one here is our remainder. That's our r of x. Okay, let me show the procedure with the use of polynomial division for this example here, for this rational function. So, f of x equals to, let me copy that again, x squared plus 2x. So, x squared plus 2x plus 1 divided by x. So if we do this using polynomial division, it would look something like this, right? X squared plus 2x plus 1, dividing that by x. Of course, this one here is x. We'll multiply that with x here, so we can subtract that with the first term. So x squared here, subtract, that's 0. We bring down 2x. We will then multiply x with 2, and so we have 2x here, subtract, that's 0 again, bring down 1. So here we can write now our answer in this form. We have f of x equals to x plus 2, which is our L of x, plus the remainder over x here. Okay? So this one, this is our oblique asymptote. Okay, so remember, oblique asymptote is just a line, right? So it's a line, but it is diagonal. And this is what we will use now to identify where the oblique asymptote is into our graph. So remember, our oblique asymptote L of x is equals to x plus 2. Okay, so we have this one. So if it's y equals to, if y is equals to x plus 2, right, that means we have the y-intercept at 2 here. And if we set, so y equals to x plus 2. If we set this to 0, then the x-intercept will be x equals to minus 2. And so we can now form the line, and that is this one here. Positive slope. Change color to blue. So this one here. Oh. Okay, I don't know how to change that, but anyway, that's our line there. Okay, so this is now the oblique asymptote. Now, in identifying, or if we need to sketch the graph, let's just create a table here. So say, for example, we'll use this one here. This is our x. This is our f of x. Okay? So, let's just maybe start with minus 2 here. If x is equals to minus 2, remember, the answer here is f of x is equals to x plus 2 plus 1 over x. X plus 2, 1 over x here. So when x is equals to minus 2, we have minus 2 plus 2 and plus 1 over negative 2. So basically it's just negative 1/2 or 0.5. Negative 0.5. If it's negative 1, this is now negative 1 plus 2 minus 1, right? So which means it will just be 0. And if it is 0, so 0 plus 2, of course, that would be the undefined, right? And that means that will be, in a way, your vertical asymptote, because it's undefined. And if it is 1, so 1 plus 2 plus 1. And if it's 1, then this will be 4. If it is And if it is 2 plus 2 plus 1/2. Okay, so that would be 4.5. So if it is 2, then this is going to be 4.5. Okay, so now let's go back here. I hope this one, no, it doesn't. Spectrum. Okay, so for the graph, because this is our oblique asymptote, let's first, so we have at -2, our f of x is negative 0.5. So negative 0.5, if this is -1 here, if this is -1 here, then when x is -2, then that is over here, right? Okay, and when x is -1, it's 0. So we have this over here. This is -1, 0. And we know that we have a vertical asymptote here because it's undefined. Okay, so which means if we connect these two things here, that will go that way. And if this is an oblique asymptote, that will go that way. Okay, so we have that one there. On the other side, on the right hand side, so when x is equals to 1, this is 1 here, your y is 4. So let's just say this is 4 here. This is 4 over here. So when x is equals to 1, your y is 4. So let's use that over here. And because this is we can even, if you look at the value here, when x is equals to 2, your y is 4.5. Also, because this one here is an oblique asymptote, you would know that this will go this way, and this is a vertical asymptote, it will go that way. Okay, and that's it. That's how we sketch the graph when, or if the function, if the rational function, the degree of the numerator is 1 degree higher than the denominator.